started now. Yeah, this is our workshop on causal inference with Javier. He's going to be our workshop lead. Take it away.
Hello. Okay. Awesome. So, thank you for coming, and we're going to do causal inference. Now, that might be a term you haven't heard before, so I'll slowly go at it, and I think we'll get something meaningful out of this. One second. Okay, so I'm Javier. First of all, I do math and physics here at the University of Waterloo, and I've been doing research and applied causal inference for the last 8 months. So this was a required slide, so we'll skip it here. Just some sort of agenda. For the first 5 minutes will be just some sort of intro, then some yeses or no on machine learning, what is it used for and what it cannot do. I'll explain what causal inference is. I'll give you some case studies, and then we'll do 30 minutes of hands-on and any questions. First thing is The Simpsons. Yeah, so The Simpsons, not the characters, but there's something called the Simpsons paradox. And I know it's totally expected. What this is you see there's a scatter plot of all kinds of Simpsons characters. Now, if you were not to differentiate between any of them and you would just have the samples, then you would see a trend line that would fit it would go upwards. But it's called a paradox because once you notice that you have different categories within it, namely the different Simpsons characters, then you can almost stratify by each character. And you find that if you only look at Bart, for example, the trend reverses. That could be very, very important to know. So that's a sort of just to build an intuition on how, if you don't think about the data you have before actually trying to make conclusions from it, you can get to very wrong conclusions, even opposite conclusions. Yeah. Now, if you've ever heard the phrase correlation doesn't mean causation, maybe you have, maybe you haven't, but this is a super fundamental thing we're going to start with. For example, if it rains, we know that car windshield wipers turn on, that we see not when we observe the world. Does that mean that when you turn on the car windshield shield, then wipers, then does that make the rain go down? It doesn't. It's an opposite cause. And then you also have some stuff like, you also have some stuff. You also have some stuff like common cause effects. So for example, and this is related to the Simpsons effect we just saw. If you look at the data of the firefighters that go to a burning building, and you want to plot the severity of that fire of the fire and the number of firefighters that you send. What you'll see is that the more firefighters you send, the more severe the fire is. And does that mean that if you want to reduce the severity of a fire, you should send less firefighters? It doesn't. It's exactly that reversal thing. And so that's an example of a common cause story, where if you're not really thinking about it behind it enough, you can get to the wrong conclusions again. And so this gets us to where we do use machine learning, which rely on correlations. Where you use it is where you can care about passive prediction. That is, if you're not really part of the system, if you're not really intervening in it in any way, it's more static in a way. That is, and there's a sketch here on the right of a guy sitting on a stick figure sitting on a couch and trying to guess what the next scene is in the TV he's watching. That's an example of the more passive prediction. He's not really interacting with the story anyway. There's an assumption in statistics called IID. That's the sort of stuff we're working with. It basically means that what we're training on or what we're seeing while we're trying to learn the trends is the same thing that we'll handle in after we're trying to actually predict them. And also when you can rely on black box models. So a lot of the times machine learning algorithms have this problem where they're hard to explain. Explainability can be hard, and if you can rely on that, great. And if you're only doing passive prediction, amazing. That's when machine learning works absolutely amazing in, but there's some limitations. So it does rely on correlations, as I just say, and it can handle more interactive environments. For example, if you're part of the system that you're training on, if you can do different things in it, if it's more dynamic in a way, then that can be very then that can be very problematic, and it depends on what kind of goal you have. If your goal is to figure out what you should do when you're part of a system, then machine learning doesn't help you much. An exception is reinforcement learning, which also has some problems in it because it might find you an optimal path in some specific, or not optimal strategy in some specific environments, but that's not, the causal inference gives you more than that. It doesn't only give you an optimal path, it can give you an understanding of the system behind it, and that can answer some more complicated questions. So it can suggest what you can do well, and I'll give you some case studies of when that matters. And also explainability and generalizability is hard with machine learning. An example is you might do you might have some very awesome data in the lab, but then when you go to real life, some of it changes, and that generalization doesn't go through. And so finally, what is causal inference? So we said correlation doesn't mean causation, but causal inference is a science of figuring out the causal relations from those correlations. So you infer causation from correlation. That's why it's called causal inference. So you do that from correlations from data you have. You also do that from domain expertise. You can do that from experiments. There's a whole way of collecting data, and it adds another level of complexity from just correlations. And so this deeper way of looking at it adds and steps up the questions you can ask. And so some of the questions you are most likely to ask are about interventions. That's different from prediction. In machine learning, you predict the next step. In causal inference, the goal is to talk about interventions. What would happen in a system if I do this? Or counterfactuals. What would have happened had I done that thing X before? Interventions are best for figuring out the best action forward or for knowing how a system would work. For example, in our earlier example, if you were had the wrong kind of conclusion, you could have turned on the car wipers in order to make the rain go down. Doesn't work. Counterfactuals are more about understanding. For example, when you ask a why question, why did something happen? Or then you're almost asking a counterfactual. What should we have changed in order to have that not happen? The scenario you were in. And so causal inference asks different types of questions for machine learning. It's not suited. It can be good for in some cases, but its best uses are not prediction, but rather intervention or counterfactuals. And that's an important point to make. Now, there's also a complexity kind of hierarchy here. The least complex or what machine learning excels at is observations, seeing associations, dealing with those. And in machine learning and causal inference, we're working with a slightly more complex kind of step in this ladder of causation. This is from Judah Pearl's Book of Why, which is a great pop sci book about this. We're just talking about interventions, doing stuff, and imagining or explaining counterfactuals. And so again, we've said there's plenty, but the main usages are of machine learning are prediction, whereas our causal inference is actual planning, action planning or understanding. Machine learning is great when you have that usage in mind, and you can have that assumption of the data not changing between training and prediction. And causal inference is good when you have some sort of domain expertise behind what's happening and you want to encode that in a model. The machine learning can be difficult, but there's also a higher variability. It can be easier in some cases. Causal inference is hard in most cases, not always. But if you want to do it in practice on some complex enough examples, it can be hard. Also, it's somewhat of an it's somewhat is exploding in the last few years, and so a lot of stuff are changing, and that can add to the how hard it is. Now, combining the two, we do want to combine the two because machine learning is great for estimating functions and that kind of stuff, which we have the usages for that in causal inference. And so reinforcement learning is causal in a way, but there's room for improvement, as I mentioned before. Recommender systems are causal in a way because you're asking about an intervention. And so you want to utilize this function finding power of machine learning to find what we call a structural causal model. This is the model behind a machine learning, behind a causal inference. This is the algorithm. This is the equation behind the causal inference modeling. So it can also be good for fairness. For example, if you want to make sure your machine learning model isn't biased in a way, causal inference is how you do that. And for generalization, if you don't have that IID assumption, and you still want to utilize the power of machine learning, causal inference can help with that. And there's been a lot of examples of that. And so just a tiny more technical about what is behind causal inference. We work with directed acyclic graphs, DAGs. They're basically, you have a bunch of nodes, each of them is a cause or an effect, and then there's arrows pointing it from a cause to an effect. And so we can see here that we have Y, which is a common cause to X and Z, X causes Z. And then if you want to ask about an intervention, then what you do is you separate all the arrows leading up to X. So for example, if you want to ask what would happen if I do X, intervene on X, what would be the effect on Z? You take out all the arrows leading up to X, you set it up you force it to take a specific value, and then you can actually see the effect on Z. And so we're going to do some hands-on. We're going to use some popular tools in causal inference. DoY, EconML are both by Microsoft. Causal ML, and Causal Next, Causal Learn are also great. And there's a lot more resources and links I have here, which I should find a way to give it to you guys. But yeah, Causal Lens is a startup, and they also do some interesting stuff for hands-on, but I don't know if we can get access to that right now. So we're going to do DoY and some others. But before we do, I'll give you some. Before we do, I'll give us some example of case studies in practice where causal inference was useful. There's a startup. There was a startup a few years ago called Babylon Health. They were an AI company that tried to diagnose your symptoms, and you give them your symptoms that they would try to diagnose your disease and what sort of treatment you should have. It was a chatbot, but they found a big problem, which was that whenever you give it symptoms of high blood pressure, chest pains, and yes, okay. So whenever you give it Whenever you give it those symptoms, then it would diagnose you with diabetes. The thing is, diabetes doesn't cause any of those symptoms. However, they had this problem that all, and the AI wouldn't know it, but if you ask any doctor, it would tell you that he would not tell you, or they would not tell you that it would be that diabetes. So the problem, so they noticed that, and they wanted to understand what was happening, and they saw that there's a twofold problem. One of them is that diabetes is prevalent in the population at large already, so it would exist with other. It would exist with other diseases at the same time, a lot in the in the general population, and also that there was a common cause to both diabetes and the diseases that would commonly cause those other diseases, those other symptoms that that so that made it look like they have a high correlation. And whenever you would actually get to a point where whenever you see those symptoms, if you were to ask, what's the most sure, if I had to bet, what's the disease that person is most likely to have, then diabetes would be the right answer. But if you were to ask, how should I treat this person in order to get rid of those symptoms, then diabetes would be the wrong answer. And so a person from our team went on to that startup, and they knew some causal inference, and they rephrased the question in order to be a more causal intervention question. And the performance of that startup went from being median in doctors in the UK at the time to being the 99th percentile immediately. And so that was a good success story. And another one is about health, more about health. But if you were 100 years ago, you were trying to figure out if smoking causes cancer, you might be convinced, or maybe you have the interest to say that smoking doesn't cause cancer, but it's the fact that there's a genetic predisposition that causes people to smoke and also causes people to get cancer more easily. Now, that's the wrong conclusion, but at the time, maybe if you didn't have enough data, then you might make that wrong conclusion. And so there's a way to test that with causal inference. And what they found was that if that genetic predisposition were to happen, if that hidden factor, that hidden cause were to happen, it would have to be so strong that it was invalidated. It couldn't be a possible explanation. And there's other ways of doing the same, of getting to the right conclusion as well, which is by introducing variables of tar and lungs, for example. Tar in lungs the amount of tar you have in your lungs couldn't be caused by the genetic predisposition. And so there's all kinds of different ways of using causal inference in order to not be mistaken by those statistics. Another example is in economics. In 2021, the Nobel Prize was won with a causal inference usage on the minimum wage impact on employment. What they used is called the instrumental variable technique, and yeah, so I won't get too much in depth into what they did, but this is just to say there's a lot of different use cases for this. And so now we're going to do some hands-on. There's either a link here or QR code. So if you can open that up. Right. I'll give it a few more seconds. What we're gonna do is we're gonna get some of so this is the notebook. What we're going to do is we're going to clone some helper files from GitHub, so just run that first cell. And you'll use those files later. Then we're gonna install a few of those libraries that I talked about, DoY, Causal Learn, and EconML. DoY and EconML are Microsoft, Causal Learn, I'm not sure, but it's also very useful. Yeah. And if anyone has any problems, there's mentors here, people that help. And we're gonna import a bunch of libraries. I don't think yeah, okay, yeah, we're gonna import all of them. And we're also gonna import those helper functions. Okay, now we're gonna use synthetic data. We're first going to just explore it before we actually know the story behind the data. But it is synthetic in order to make this, for us to not have to do all the pre-processing and stuff like that. But let's look at it. So this is a data frame. We have about 150,000 samples. And we see some very weird, we see some variables. The first one is whether is called is senior. We see that it's a binary variable. It's either 0 or 1. And that, yeah, and is senior, that tells us that it's a variable determining whether someone is senior or not. Then we have sale calls. So it looks like a business problem. They have a number of sale calls, and it's an integer from 0 to 14, so it's ordinal as well. And then we also have the number of bugs faced. We have it's from 0 to 10. We have the monthly usage, so it seems like it's the monthly usage of a customer from 0 to 32. We have a consumer trust, so that could be a score of how much does the consumer like us or trust us or anything like that. Then we have a variable about the interaction. How well is that interaction? We see that it's continuous. We can deal with that with multiple ways, but we might want to either split it up into different bins, or we might want to keep it continuous. But it's from 0 to 1. We have a discount and a renewal. So the story is behind this data is you're a company. You have some data about your product and about your users, and you want to find out whether someone will renew or not the service, and also what you can do in order to increase your renewal rates, and in a way, what you can do in order to satisfy your customers and make your product better. And so how we're going to do this to handle this problem causally is we're going to treat discounts as a treatment to a user and find out whether intervening on discount will increase the likelihood of someone renewing or not. And so there's a few graphs here that we can look at in order to see if we can make sense of our data. The first one, we see that about 75% of people are not seniors, and that a lot of the data isn't exactly normal. And this seems a bit weird also, and this is definitely skewed. This is also, there's all kinds of stuff we can see here. And so let's look at our actual data, or at least some samples of it, and we can try to make sense of this. So for example, if someone is not senior and has had one sale call and faced 3 bugs, uses the product 6 times a month, and has a somewhat high trust us, maybe it's through surveys or anything, but their interaction is just about 0.6. If we give it a discount, he'll probably renew. That's the sort of problem we're dealing with. And if there's another person, we can read it in all different ways. And so what we're going to do, the first thing we're going to do is we're going to do causal discovery. We're going to use the PC algorithm. It's an algorithm that uses conditional dependencies between samples in your data to find out what causes what. Now, there's problems and assumptions that you have to make if you make this algorithm. There's other algorithms that we won't get into, but the two big things is that there's no this is a bit jargony, but no unobserved latent confounders. What this means is that there's no variables that are hidden that causes two things or causes multiple things, or that are a common cause to other stuff. Now, we're going to do this algorithm, but we're going to I'm first going to warn you that the PC algorithm doesn't always give you one DAG or one causal structure. It can give you a class of causal structures, and that's this algorithm specifically. And after that, what you can do is you can use other algorithms to narrow it down. You can use your domain expertise if there's an edge or an arrow that doesn't make sense to you, or if there's an obvious direction. For example, if you're on the rain and car windshield wipers, it won't find the direction between the two. You can use your domain expertise in order to fix that. So we're going to run this. And this is what we get. We see that this is a DAG. This is a directed acyclic graph. It's a causal structure. We see that on the left or on your right, whether someone is senior or not, affects their interaction levels. How many times people get sales calls also affects how well they like the interactions. If people are bugged, maybe they interact less. But you also have to realize that you don't fall into some sort of Simpsons paradox, where maybe someone, when they're not a senior or they're younger, maybe they want to get less sales calls, and maybe that trend inverts when someone is older. And so we can see the other parts of the DAG. The amount of bugs faced affects the discounts. It seems maybe, and then the amount of monthly usage also affects the discounts. The consumer trust that is not caused by anything else here, but affects the renewal rates, and the discount that we're going to intervene on affects renewal. This is what the PC algorithm gives us. And so if you see something that doesn't make sense to you, you can also directly intervene on that or directly fix that graph differently and manually fix it. Or if we didn't have an arrow in one of those edges, then you would want to add an arrow because it couldn't find out the causal direction. And so there's a lot of ways to do that. And now we're going to compare our results with the ground truth. Now I made this is a synthetic data, so I know what's behind it. And this is the ground truth, and it is the same. Or you can look at it on your own computer and make sure it's the same. But there's more questions that you want to ask. First of all, and that we don't really have time to. The first thing is, how does the PC algorithm work? It can be somewhat technical, and it's not always that obvious. What are its limitations? Does it always find a unique DAG? I just told you that it doesn't, so you know the answer to that. It finds this thing called a Markov equivalence class. Just means it doesn't matter. You can click the link if you want to find that out. And what are the other popular causal discovery algorithms? It turns out that there's different types of causal discovery algorithms. called score based and constraint based. What does that mean? When do you use either of those? Those are all sort of questions that you want to ask if you want to go deeper in this. And now we're going to actually estimate our treatments, our interventions. And so we're going to treat discounts. That is, we're going to intervene on discount, and we're going to see how that affects our outcome, being renewal rates. And so we're going to do some somewhat introductory. So we're going to do this very simply. We're going to just split our data to train and test, and we're going to use the causal forest estimator. That's one way of estimating the causal effect. There's a lot of different ways. Some of them are more sophisticated than others. Some of them use neural networks. Some of them use just some of them have used mathematical tricks and stuff like that. But we're going to use this for now, and we're going to see what it gives us. And while it's running, does anyone have any questions?
Yes, I guess this is what related to systems modeling. Systems we have the graphs, directed graphs for the different relationships between different variables. Yes, but for systems modeling, you do have cyclical graphs. So I guess that's the difference.
Okay.
Loops are permitted for systems.
Okay. I don't know about systems modeling, but it sounds like it would make sense that it would be there. If you want to understand a system and model it, then this sort of cause effect or what causes what in your system is crucial. Now you can have in more complex applications or more complex theory, you can have cyclical relations, but that can be very complicated, and so we're not going to get into that now. But this is a thing called an indefinite causal order, and there's a lot of research done on that, specifically in the more quantum applications, and that can be very, very cool, but it's also a lot more research than and theory than can be right now. Yeah.
I assume it's easier for time series models because we do have like leading variables that you can use to predict off of, but for regular regression, classification might be harder, I guess.
Yeah. And you had a question?
I had a question also about the cyclic causal, but another question is, you said earlier that you need to worry not to fall into the Simpson paradox in the early one of the seniors and the sales calls. How can you avert it? How can you not fall for it? What do you do?
Well, there's multiple ways. So the Simpson's paradox is somewhat of a known example on how relying on correlations can be difficult and can lead you to the opposite conclusions. Now, complex enough neural networks are able to are smart enough to pick up on that if you have the right variables in your training. And so the points that you should get out of this most is before we do anything technical, is that sometimes thinking about the thing behind your data, that what people call the data generating process, is super, super crucial, and having a sort of understanding of what's happening behind all those numbers can be so useful. And so the first thing you want to do is actually understand what's happening behind your data. And in that case, then you're going to cover the cases where you are going to send less firefighters into a fire. Now, in more complicated ways, Simpson's paradox specifically, if you have the right feature, if you do the right feature selection, then Simpson's paradox will not be there. And if you use regressions, it would be there. But if it's complex enough architectures, it wouldn't be there. In causal inference, once you put it in a causal structure, then even a very simple causal inference problem would immediately alleviate that. But the first thing you want to do is actually make sure you understand some sort of story behind your data, and you can do that if it's a bunch of if it gets complex, then the first step could be causal discovery. You can, to have some sort of idea of a causal hypothesis behind the data generating process. You can do that with those algorithms or others. And that could set you up into starting out your data task well. Yeah, so this took a minute, but does anyone have any questions? Other questions? Okay, so we're just gonna interact with this a little bit and play around with it. And what we're going to do is we have this user. This is just an example, but there's multiple others of that is not a senior. A single sale call, they faced 4 bugs and they have a monthly usage of 10. What 10 means, it might be 10 times a month, might be 100 times a month. There's all kinds of ways there's all kinds of interpretations, but it's 10, and I think it was from 10 to 26 or 36 or something. So we know it's about the middle. And now we have a consumer trust of 4 and an interaction level of 0.8. Now remember all the limitations on those values. So from interaction, it could be from 0 to 1, and that's 0.8. So they're pretty. Their interactions with our product is pretty well, and we want to see what discount we should give them. And so the baseline is 0. That doesn't change anything. But if the output is not the probability of renewal right now, but it is the incremental change in that probability. And so now if we give it a discount of 1, then we can see how that changes the probability, and it's the opposite. Now that's not what we expected. And so we can mess around with this more and see how how that changes. And so you can mess around with this for a few minutes, and I'll walk around to see how it works on your end. But this is the sort of stuff we do, and you can also change the treatment if you want to ask different types of questions. For example, maybe you want to increase the support a user might have, and in that case, that means you don't change the discount rate, but you treat the interaction level. And so you can do all these things. Some stuff are not intervenable, like the age of a person, but this is the sort of process you go through. And now there would be further questions, or you could actually check the treatment effect levels between giving someone discount 1 or no discount, discount 4 or discount 1, and depending on the cost of each discount, you can find this optimal strategy. Now, further questions that you might have is, what are the different machine learning methods of estimating treatment effects or interventions? What are their limitations? And there's also non-machine learning estimating methods. What are they? Can you estimate interventions and counterfactuals through limited data? So our data is not infinite. So what are the uncertainty quantifications behind these sort of stuff? How do we suggest optimal treatments? So we do want to keep in mind the cost, the potential savings, and the incremental effect. We want to keep that all in mind when we come up with anything that when we want to figure out our next best steps forward. Then how can we come up with a discount program strategy? So in our example, we cared about discounts and how that affects the renewal rates. So you can use that to come up with a strategy, and then an example would be, should we give discounts to people who would otherwise already renew? Well, those are sort of strategic questions you can ask. Then what other possible treatments do we have? We saw that the Interaction levels were also treatable, and so we can mess around with those and do some sort of interventions and see how that affects our renewal rates. And another important thing is we have our past results. We know what sort of renewal rates and discounts we gave people. What would have happened had we used our strategy that we just came up with in the past? Would we have what would be the results? And so these are the sort of problems and questions you can answer with causal inference, and they're a lot harder, and sometimes you get to the opposite conclusion if you're only doing predictive modeling. And so lastly, there's some fundamental DAGs with examples of cases where they apply. These are some of the most well-known kind of DAGs that you have to work with if you ever actually do this. If you go further, now I gave it a story for each of those just for it to make sense. But for example, that someone might be in an educational program. There's all kinds of different examples. And each of these DAGs have a sort of name that they're known as. So this is confounding, and this is a collider, and mediation. There's all kinds of different examples. So you can look around this and play with the treatment estimations. You can give it different number of trees in the forest. This is just a number that you can change, or you can also, anything that you want to do here, you can change. Just make sure you copy the file and change it on your end. And I'll walk around and see what you guys do. So any last questions? Awesome. Thank you.